Hello everyone. In this video we are going to look at a method that is used a lot in machine learning, computer vision, and so on. Anytime we are trying to fit a model to a set of data and there are lots of outliers in the data, so the model that we fit, if we go with regular methods without doing this algorithm here, might be very bad fit, might be inappropriate model. So this algorithm is called random sample consensus, or RANSAC, which you might have used without knowing that you did. And specifically, for instance, in computer vision, when we did feature matching, and we found lots of features between two frames, and we wanted to see which one of these features that are matched between the two frames are good match, and we call inliers, and some of them are bad matches or outliers. We use this RANSAC, right? Just to show you that, here is from scikit-image.org. You can see I have two chessboards that I did point-to-point correspondence, right, corner to corner, so these are Harris corners. And if you look at this feature matching between the two frames, you see that some of them are not correct. Like which one? Like, for instance, if you look at these bottom ones are some of these top ones that are not good. Like, look at this one here. You see, this point is on the edge, but if you see where it is matched to this one in the second column, right? Or if you look at this one, this is very clear. Again, look, this is the last column. This is the second column. So some of this feature matching, although it thinks that the feature descriptors are very, very similar for those feature points, but it is a wrong match. So if I want to find the homography between these two, right, we should get rid of these outliers and then just do the model fitting between these inliers, between the good matches. How do we do that? Another example is if we want to, let's say, do a simple curve fitting, right? We want to do a regression, simple curve fitting, linear regression. And let's say this is the data that we have here. And this data that I have, and most of this text is taken from Wikipedia. So let's say this is the data and you want to fit a line to this data. So you see the majority of the data, or a good portion of the data, not majority, a good portion of the data is on this line, which I can see, but there is a lot of noise. There is a lot of outliers outside this line. So if I want to use my list of squares curve fitting, right, this is what the list of squares will give you, this red curve here. And I just wrote a code for that I'm going to show you. So I typed all the data in Matlab and then did list of squares curve fitting, and this is the result. You see that it's not a good fit. Clearly this red line does not match the line that should really pass through all of those points. But if you do RANSAC first finds the inliers for you, which are all of these circles that inside of them there is an asterisk, and say only use these data for a line fit. Now the line that it fits is this green line, which matches our intended model a lot better, right? Because it says all of these other blue lines are outliers. I do not need to count them into my model fitting. Okay, so how does this important algorithm work? Let's talk about that. So this method, the idea of it is what you can see here is called repeated random subsampling. Okay, repeated random subsampling is the basis of it. So we are not going to fit a model, in this case a line, one time with this data. What we're going to do is each time we're going to go and grab some of these points. You know, for fitting a line, you really need two of these points. So each time we're going to go and grab two of these points. So we create a sample. Let's say first time I get this data and maybe this data. And I fit a line to them right here. And then what? Then I use a threshold which will tell me how far off from this line the data count as inliers, and outside that band it is an outlier. So for instance, I pick a parameter, it's a hyperparameter, which here we call it hyperparameter T, or a confidence number parameter. So I say anything between, let's say, plus minus 0.2 of this line is an inlier, right? So I choose that. And anything outside that is an outlier. And then I count how many inliers and how many outliers. So here I say here, 1, 2, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Maybe count this one. Ideally, if it's on the line, no, but let's say it's inside, 15. So my inliers for this model is what? Is equal to 15, the number of inliers in this, when I use these two lines, these 2 points. Then I repeat that. Next time I grab another 2 points. Next time I grab, let's say, this point and this point. Again, I fit a line, right? Let me use the line here. Maybe it does a better job. So then I grab a line again, right? And then what? Then again, I draw that band here, right? Something like what you did for support vector machines. Remember, you always had a band and the goal was to maximize the band, right? Here, you don't maximize the band. You fix the band at a specific width, and you want to maximize the number of points inside the band. So here, count again, right? You see, if even I count the point on the line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So with this one, the number of inliers is what? Is 10, right? And then I repeat that, and at some point I come and grab what? 2 points, maybe this one and this one here. If I do that, now let's draw a line between these two, something like this. If I draw now the parallel lines at distance t, you're gonna see that I have what? I have a lot more inliers than probably any other model, than any other line basically, or model here. So now if I count, it is gonna be more than any other probably set of 2 points. And I say, hey, this is the good model. I pick this black line as my model, and then anything outside this band, which are all of these other blue lines, I call them outliers. And now I only fit my model to what? To, now, do I pick this line once I get rid of this data? Once I said, hey, look, let me cross them. So once I said all of these guys and all of these ones are outliers, now what do I do? Is it done? Do I pick that initial line here? Do I say this one is good? No. Now I say all of this data inside the band are my data, my inliers. Then what? Then I refit the line to all of these points instead of just these 2 points. Now I try to what? I try to fit my model to all of them, and this time might be a little bit off from this. It might be something like that, maybe. Okay, if you do a list of squares now, but here clearly this is the best thing that you can possibly have, right? So again, anything inside this range, we call them finite inliers, and anything outside of it, we call them what? Outliers. So you see, the idea is very simple. Each time randomly you pick 2 data points, you fit a model, so that's random sampling. Why do we call it subsampling? Because you are not going to use all of the data points to fit that line each time, only use 2 of them or a few of them or a portion of them. So you are subsampling, and you keep repeating that until you get to the model with the maximum number of inliers. So that is the essence of RANSAC. One of the good things about this method is it's non-deterministic. Okay? So it can only produce the result for you with some certain probability, with some certain confidence. Okay, and that confidence is actually one of the parameters that in Matlab, when you use the command RANSAC, you can pass that confidence parameter to it. Okay, and I'll show you what's the relation of that confidence to the rest of the parameters in the model. Okay, and if we want to have some definitions for inliers and outliers, we say that inliers are the data whose distribution can be explained by the model and model parameters, but outliers are the data that do not really fit the model. Okay, so I want to show you the Matlab code, but before that, let me just briefly go through the steps of RANSAC, which again I borrowed from Wikipedia. So the steps are this. You select a random subset of original data and call this what? The hypothetical inliers. The number of samples in this subset must be sufficient to fit the model, and it's one of the hyperparameters. So for instance, when we fit a line, we can use only 2 data points, or we can use more if we want to, right? Because it's a list of squares. So if we want, each time we can grab 3 points and fit a line, but minimum is 2. Okay, next. A model is fit to these hypothetical inliers. Then what? Then all of your data are tested against this model. Using a what? Using a specific either loss function or a confidence parameter. Here, the width of that band, for instance, this is another hyperparameter, we might call it T. And then what? And then those data that will fit this specific model, those inliers that fit this specific model, we call them the consensus set. So now you see the reason for calling this random sample consensus. Okay? Then what? Then we say this model is reasonably good if sufficiently many data points have been classified as the consensus set. Okay? Now, when it says sufficiently many, that can be another hyperparameter. So this model keeps going, keeps repeating until at least a minimum number of inliers are what? Are selected. So that could be another parameter if you want. So keep doing it until at least I have in one of these models D inliers. But typically this model, instead of that, will keep going for a fixed number of iterations, which is another hyperparameter. And then it picks what? The model with maximum number of inliers. So you can either write it as a for loop for I goes from 1 to this K, get the number of inliers for each and every one of the models, and then go and pick the one with maximum, or you can use a while loop and say keep going while the number of inliers in the consensus says is less than D. Once you reach D, then stop. Okay, so you can either use K or D, and the way Matlab code is written with K. Okay, so it picks the maximum of them. And finally, once the best one is selected, or the one with at least minimum D inliers is selected, now you can further improve it by re-estimating it using all of what? Using all of the data points now. As I said, this is the last step. I fitted this black line with only 2 points, but now that I have all of these inliers, I will fit the line one more time to get a more robust estimate. Okay? And this is the essence of what? The essence of RANSAC. So, what is the command in Matlab? Let me show you. So here are the data that I just showed you in that plot. And first, I do a simple list of squares line fitting using the command polyfit. So I pass x, y, and the order of the polynomial 1, which is a line. And not only I plot the data, I also plot the fitted line in red, right? So if I go ahead and run that for you, you see that the list of squares is not doing an amazing job, right? Here, look. Because the data has a ton of outliers compared to that original line, a lot of noise. So you see, this is not a good fit. But now I use RANSAC. I combine x and y into a matrix points. I give it the hyperparameters. I say the minimum number of points you need is 2. The width of that window is 0.1. You can use 0.2. The narrower you choose this, typically the more iterations you need to have, okay, to get to the D. But if D is not of importance, is just grabbing the best is the importance, typically you might have a small number of inliers or consensus set per test. Okay, so you should not pick this very, very narrow, because if you do, then your model is not going to be robust, and the algorithm might give you an error says, I could not find enough number of inliers. And what is the minimum number of inliers that each model need is equal to n. Okay, so D in Matlab is equal to n, the minimum number. It cannot go less than that. And here I give it the maximum number of iterations, 2000. The more iterations you use, the better, more robust results you're going to get. So these are the parameters I use. Then you need a function to fit the model, right? You need to tell it how to fit the model. And here we simply use the polyfit command. So this is a function handle, this fit line function. This is the, in general, fit model function is this one. And here we are using the Matlab polyfit because that's the best one. And then you need to evaluate a function. You need to have an evaluate function to determine, like when I say this is an outlier, why do I say that? Because the distance of this point to this black line, this distance is what is more than this t here, right? So I need something to calculate for me what? That distance. And tell me in each part which one is the inlier, which one is what? The outlier. So I need the distance function. And so here you see that the distance that is used is what? As you can see, this is basically sum of the actual y's minus the fitted y's, right? Squared, and then the sum of all of those squared. So basically sum squared error. This is the distance. Okay, so here the distance is not really, if you see a model and points, okay, this is sum of the square, so it's the distance square, not just the distance. And then you see, use the built-in Matlab RANSAC function. You pass to it the points, the model fitting function, the distance function, the minimum number of points, that allowable distance for inliers, maximum trials, and k. And this one will return two things to you. One is the index of the inliers. It says what are, which points are going to be the final inliers, the best model. Just the index of them, not the points directly. So if you want the points, you have to pass this index to the original points to get the inlier points. And it gives you the final fitted model RANSAC. So here, when I got these indices, I pass them to the original data and get my inlier points. And then on those inlier points, I plot a black asterisk. So you can see on those blue circles, which one of them are the inliers of the final best fitted model. And you see here that only these guys are the final ones. The rest of them are outliers. Okay, yeah? Then what? Then once you have this model RANSAC, which is just basically two parameters, right, of the line, I can go ahead and I pass all of these inlier points, right? All of these inlier points, 1 and 2, I can pass them. So if you want, I can say inlier points of 1 and 2. And then what? And I refit the line using all these inliers. And you see here, I plot the final best fit line on the top of the original data. So if I run the whole thing all together, you can see that, look here, that the RANSAC, the line fitting using RANSAC is gonna produce much better results. Now, if I change this 0.1 to 0.2, there is a chance that I can bring in more data, or maybe not in this case because these outliers are far off. But if I make it 0.5, probably I can bring in some more of this data and make it not so good of a fit. Let's do 0.5, see what happens. See if I can get more inliers. You see, now I got more inliers. These guys are all counted as inliers. And now you see that this line is what? Is not going really in the middle of the data because this confidence number I use is too big. Okay, but still with that, still much better than least squares, right? So you can change this number. Now, as I said, there is one other parameter in RANSAC. If you look at it, RANSAC not only takes data, fitting function, distance function, sample size, and maximum distance, right? It can also be given some number called the confidence, which is between 0 to 100, and the bigger it is, the more tests it is gonna run to calculate what? To calculate the required confidence. So if you pass it the confidence, then don't give it the maximum number of trials, okay? Let's go back to the code. If you give it a confidence, then don't give it this K, because one of them is really needed. Now, how are they related? Let me show you. So if you look into the documentation of this RANSAC, so I went inside the RANSAC. This RANSAC is using this function MSAC. And if you look inside MSAC, there is another function called compute loop numbers, which if you open it, this takes the sample size, the confidence, the point numbers, and inlier numbers, and it gives you N, the number of required tests, the number of required random samples. Okay, and this is the formula for it, as you can see, which I typed for you here. So the number of tests, N, right? K in this case, let me write it as K. This K is equal to what? This is equal to ceiling of a numerator over a denominator, where numerator is like 10 of 1 minus confidence. So although the confidence you pass to it is between 0 to 100, but then Matlab will divide it by 100 for you. Okay, so make it between 0 to 1. It's a probability. This confidence is a probability. It has to be less than 1. But in the beginning, you can just pass to it a number between 0 to 100 instead of between 0 to 0.1. So numerator is like 10 of 1 minus confidence. Denominator is like 10 of 1 minus the probability of being an inlier. And what is the probability of being an inlier? It's the number of inliers for that test over the total number of points that you have for the entire data to the power of what? To the power of N. And N was what? N was this minimum number of data points you need to fit. So in this case, it's a square. It's a 2 in this case, right? So you see that K can be determined from what? K can be determined from basically your t, and you might say, where is t here? I don't see t. Well, what t will affect is this guy here, the number of inliers. The bigger the t, or the bigger the t, the bigger the number of inliers. Okay, right? And that is going to change everything here, including the number of tests. Yeah, it's conversely going to affect it, because p inlier is going to go up, this whole thing is going to go down, and so the whole k is going to drop. So if t is going to go down, then you need more tests. If t is going to go up, you need less number of tests. Okay, so t and k have a kind of opposite effect on each other, and they move in opposite directions. So I'm going to let you download this demo code that I wrote using Matlab built-in functions and play with it. Feel free to change the data to whatever you want and see the result of that. And one final thing that you might be curious about is, what is this model RANSAC? Let's just look at it. This model RANSAC is literally what that coefficients return for the best fit. And you might say here, when you fit that again with this polyfit and call it model inliers, what are the coefficients in this model inliers? And you see that they are not exactly the same. So seems like Matlab is not really doing that last step, which is fitting now the line, in this case, to all of the final inliers one more time. So it's just the best that it got, and not the final robust one, which is used using all of the inliers in the band. So here you have to do it yourself. You see that these two numbers are not the same as these. So once you get your model from the RANSAC, don't use this for the final plotting, but get your inliers from this inlier indices, pass them to your function that fits the model again, and get the final coefficients or parameters of your model. Okay, so this is what I wanted to explain to you. Hopefully it was useful to you, and I'll see you in the next video. Thank you.